Welcome to this lecture on prediction error models. We will discuss one step ahead prediction error model in this lecture. We will consider different noise models. We will show one example and a Scilab code. Here is the planned model that we have seen before, and we have taken Vn here in this equation. Yn is the sum of two terms here, one that comes from the plant, the other one is the noise Vn. Now we will see what is the best estimate that is possible. We will indicate the estimate by hat, and this symbol says y of n given n minus 1, that is you have everything up to n minus 1. Based on that you estimate y at n. Because it is estimate, you have a hat here. Now the first term is deterministic, so you write it as it is. In the place of v, which is stochastic, we have a similar expression v hat of n given everything up to n minus 1. We will look at the expression for v next, so that we can get v hat. In fact, I would want you to write this down. What is in blue here, we are going to require this 2 slides later. So let us consider the noise model, which is Hn convolved with Cn, and we can take the leading term of H to be 1. So as a result, in the place of H0 I will put 1 here. Only the term corresponding to H0 is taken out, all other terms are here. And of course if H of 0 is not 1, you can accommodate it in the variance of C. Okay. So what is the best prediction of V? Is its expectation, and this V has two terms. Recall that it has two terms here. So we have to estimate this and also estimate this. So estimate of the first term and the estimate of the second term. Now because C is white, the estimate becomes 0, and this concerns terms which already happened, because n minus 1, n minus 2 and so on, these are the terms that occurred previously, and hence these are deterministic, and as a result we see the expectation to be this summation, which is nothing but what we started with minus the first term. As a result it is Hn convolved with Cn minus Cn, which was the first term. So we have this expression. So this is the estimate of the noise. So this is the estimate of the noise, or best prediction of noise. In mixed notation we write it like this, where we use, instead of writing Hn convolved with Cn, we write it as Hz into Cn. What I mean by this is this expression. So whenever I write like this, I mean this, I refer to this as the mixed notation, which is used extensively in the textbook. So I write it as Hz minus 1 into Cn. I can common factor this out and recall the expression for Cn. Cn is H inverse into V, so I can write this expression, and I multiply it out, I get this expression. It is possible in the noise modeling that we can choose H and H inverse to be stable. It is beyond this course to go into these details, so we will accept this. So let us substitute in the expression for y hat. Recall the expression we had earlier in blue 2 slides ago, and this is that expression. In that you substitute for v hat. Okay, we will replace, in the place of v, we will replace v hat, and I get this expression. So I get 1 minus H inverse into, in the place of V hat, the expression that we derived here. This is that expression. When I multiply it out, what happens? Notice that I have a minus G into U minus, here it is plus G into U. So this factor cancels this factor. When I multiply these two, I get 4 factors. Out of that, 1 is gone. So you have 4 plus 1, 5. Out of 5, 2 are cancelled. So you should get 3 terms when I simplify it, and here are the 3 terms. There are 2 terms here, and the third term is here, and this term corresponds to H inverse multiplied by G into U. Okay, so you can think of this into this, and this yn into this whole thing which is given here, and 1 into this cancels this. You can multiply this and verify that this is indeed correct. Okay, we will make use of this expression subsequently. So this is the one step ahead prediction model. We call it one step ahead prediction model because we have all the terms up to n minus 1, and using that we are predicting what happens one step ahead. So this is known as one step ahead prediction model. Now we will consider a general model where we have polynomials in Z inverse for A, B, F, C, D and so on, and these are given in the form of the following polynomials. They are given here. Only thing to notice is this BZ starts from Z inverse. That is, there is one delay here, at least one delay here. So the constant term of B is 0. So the transfer function, planned transfer function is strictly rational. And there is at least one sample delay before the input affects the output. Let us consider an example of this type. Then the prediction model is what? Recall the prediction model that we arrived at a couple of slides ago. Here we have to substitute for G and H and we will get the prediction model. Now let us take FIR model where we have G to be equal to B and H is equal to 1 here. So when I substitute here, the prediction model for FIR is this. Remember, this is exactly the expression I used in the previous video. Instead of B, I had used G directly. So whatever we did in the previous video where I just ignored C is perfectly consistent with the one step ahead prediction error model that we derived in this video. Let us consider one more white noise model, ARX. Here is the prediction error model and the ARX model is given here. We will discuss more about ARX and so on subsequently. For the time being, let us just accept this terminology. So as a result, when I take this A to the denominator, B by A becomes this planned transfer function G and H becomes 1 by A. When we substitute in this expression, we get the prediction error model for ARX, which is obtained here. When I simplify it, I get this expression. So here is the prediction error model for an ARX model. Similarly, you can arrive at prediction error models for lots of other models also. Now let us take an ARX model where A is given as a polynomial of this type, B is given as another polynomial. When I substitute and take all the terms corresponding to the past y's to the right hand side, I get an expression of this type. Now C of k appears in the equation it appears in the equation, it does not appear in the output as we saw earlier, because now it is not just the output, you also have the past outputs. So we call it as an equation. So CK appears in equation as opposed to appearing in the output directly. So we call this as an equation error model. These are some of the terminologies that arise frequently in the topic of identification. Let us now consider an example with specific numbers. Generate input UN, white noise Cn, and the corresponding output Yn of the ARX model. From the input output data, determine the underlying ARX model. This is identical to the problem we discussed in the previous video. There we studied an FIR model. Here we are studying an ARX model. That's the only difference. So for this, I'm going to use this Scilab code arx_est.sce, which is given here. CRA is the function that we used in the previous video also, which I displayed earlier, so I would not show it now. But rmac1.sci is used here. Here is the code listing. All these are made available to you. You could go through that, you could execute them. When you do that, you get the impulse response coefficients to be like this, and let me write this in the model form. Here is the model, and here is the estimate that we arrived at, and notice that the estimate is very close to what we started with. In the place of 0.5 we have 0.4878, in the place of 0.6 we have 0.604, instead of 0.2 we have 0.1887. You see that the estimate is very close to the model. Of course, we need to validate the results. For the estimates to be acceptable, ACF should be an impulse function, autocovariance function. Moreover, CCF should be 0, cross covariance function should be 0. That is shown in the next page. You can see the autocovariance function to be impulse. I am not sure whether you can see this here. You can see that at 0 you get the value of 1, and everywhere else it is 0, and similarly cross covariance function is 0. Whatever is within this yellow box is statistically not different from 0. So as a result, you can take all of this to be 0, and here is the model with model parameters and so on. With this, I have come to the end of this presentation. Thanks for joining. Goodbye.